Introducing VL Explore. VL Explore is a novel navigation pipeline for simultaneous exploration and target discovery in unknown environments. Unlike most existing VLN systems that rely on traditional SLAM and path planning algorithms, we propose a model centric approach for simultaneous exploration and target discovery. The proposed pipeline only uses visual embeddings generated by a visual encoder from an RGB feed, requiring no extra sensor modalities nor any other traditional algorithms. It is modular, configurable, and extensible. The perception front end acquires images from an RGB monocular camera. It executes customizable slicing strategies and encodes each sliced tiles into visual embeddings using the CLIP visual encoder. The visual embeddings are then sent to correlation middlewares. The vision correlation middleware accumulates a familiarity database in real time. It correlates new frames with existing ones and produces a familiarity score. The vision language correlation middleware correlates visual embeddings against precompiled prompt databases. It produces navigability score for visual navigation and optionally produces target confidence for target discovery. The correlation scores are passed to the decision backend. The decision backend translates the scores into actual motion of the robot. We implemented 3 operational modes: normal navigation, target lock, and look around. A software driver stack is developed to support real-world experiment with the proposed architecture. To meet the performance demands of real-time on-device inference, we designed an unmanned ground vehicle platform, OpenRover. It is a customized platform for general-purpose VLN tasks in the real world. It is designed to be low-cost, modular, configurable, and extensible. Despite its relative low cost, OpenRover's unique in-wheel drive system and independent suspension design allows it to work with challenging terrains, significantly expanding its range of application. We performed extensive experiment with our system. We set up a maze in a shared high bay lab space. We select 5 locations, northeast, northwest, center, southeast, and southwest, as the start or target location of a task. We performed 3 tests on each of the 20 combinations. For demonstration, we animate and narrate one of them. The robot starts from the southeast corner of the map. Its target is located at the center of the map. The robot performs an initial look around at the start of a new task. It selects to head to north according to perceived environment. The robot enters normal navigation mode. Its motion mixer is actively working to help the robot to avoid collision and keep exploring. The robot stops because there is no navigable path in front of it. Luckily, it is able to find navigable space on its left before trap signal is activated. The robot navigates itself through the corridor. It speeds up because it perceives an open space with very high confidence. The robot stops in front of the wall. It cannot move any further because there is no navigable space in its field of view. Therefore, a look-around action is initiated. In the look-around action, the robot is able to perceive its surroundings. It selects to head to a direction that leads to a different location than where it came from. The robot proceeds to the center of the map. It transitions into target lock mode upon detecting the target. The robot slowly approaches the target. The target is identified and the mission is completed. In order to better understand the performance of our proposed system, we simulated various map-traversal and pathfinding algorithms for comparison. Simulations are performed in our custom-developed 2D robotic simulation framework. For map-traversal algorithms, we implemented random walk, wall bounce, and a custom-designed wavefront simulation algorithm serving as the baseline metric. In the random walk simulation, the robot starts with a random heading. It randomly selects a new heading whenever it hits an obstacle. In the wall bounce simulation, the robot starts at a given heading. When running into obstacles, the robot bounces off it according to the normal vector of the impact point. In the wavefront simulation, we simulate a probability wave propagating through the 2D map. The wave is dominated by the wave equation, which is commonly used in physics simulation. A drain field is placed at the destination point. It absorbs probability wave and reduces the overall probability remaining on the map. We use the travel distance of the first contact point as the baseline for comparison across all results. For pathfinding algorithms, we tested the bug algorithm family. It's worth mentioning that all bug algorithm requires previous knowledge of the target location. With this extra information, they have an unfair advantage over our proposed VL Explorer and all map traversal algorithms. Bug 0 always heads to the target when possible. Otherwise, it turns to the predefined direction to avoid the obstacle. Bug 1 heads to the target until encountering an obstacle. It then circumnavigates the obstacle and records the distance to target along the path. After closing the loop, the robot reverses on the same path it circumnavigated to the point with lowest distance to the target. Similar to Bug 1, Bug 2 also circumnavigates an obstacle upon encountering one. In addition, it keeps track of a center line connecting the starting point and the target. It resumes heading to the target when it encounters the center line during circumnavigation. Experimental data is collected from 60 real-world experiments and 2,140 simulation runs. All results are aggregated into the plot of success rate versus mean inverse trajectory length. In order to better understand the results, we introduced a new metric, entropy preserving score, that quantizes the amount of information available to an algorithm, providing more comparability across different experimental setups than the existing SPL metric. Comparing with existing vision language navigation systems, ClipRover uniquely requires zero prior knowledge of the task space and operates solely with a monocular RGB camera. Additionally, most comparable systems do not directly produce low-level motion commands, but instead generate high-level instructions that depend on traditional localization and navigation system for motion execution. In contrast, ClipRover directly outputs low-level motion commands, eliminating the need for auxiliary control and localization systems. This feature makes ClipRover particularly suitable for rapid deployment on low-cost robots with limited computational and sensing resources. Thank you.